In this video, I want to talk about a set of assumptions which, if they are satisfied, then least squared estimators actually have some very nice asymptotic properties. So that's the property of OLS as n tends to infinity. And the good thing about these assumptions is that they are, in general, somewhat less restrictive than those of the Gauss-Markov conditions. So just to remind ourselves, the Gauss-Markov conditions are the set of assumptions under which the expectation of beta hat least squares is the true parameter beta. And not only is our least squares estimator unbiased, it is also what we call efficient. So there are no other unbiased estimators, or no other linear unbiased estimators rather, which are more efficient than least squares. The set of assumptions which I'm going to talk about here are the set of conditions under which beta hat least squares, as our sample size tends to infinity, then the value which beta hat least squares actually outputs tends towards the true parameter beta. And not only that, we can actually go about doing sort of normal inference, and because of the fact that beta hat least squares actually behaves kind of normally, in terms of it behaves kind of normally distributed as our sample size tends to infinity. Okay, so what are these set of assumptions? Well, the first set of assumption is that we have a model which is linear. So there's no difference between that and the Gauss-Markov conditions. So this assumption essentially says that we've got a model which is something like yt is equal to alpha plus beta 1 times x1t. So the 1 here indicating one particular independent variable. And then beta 2 times x2t. So the 2 here indicating it's like a second independent variable, plus some error ut. So that's just a standard linear model because I don't have any sort of beta 1 squared or beta 1 times beta 2 or anything like that. The second assumption is different to that of the Gauss-Markov conditions. And I'm not going to speak about it in sort of depth here. I'm just going to state it, and we're going to cover it in much greater depth in future videos. But just to say that our time series have to be both stationary and something which is called weakly dependent. And as I say, don't worry, you probably won't understand what these mean now, but we are going to cover off what this actually means in future videos. The third assumption which we require is that we have an expectation of the error term ut given the values of all the independent variables at that particular point in time has to be equal to 0. And note that this is less restrictive than the strict exogeneity assumption, which said that the expectation of ut given all my sort of independent variables xi at any time s had to be equal to 0, because this relationship here had to hold for all s, including the circumstance where s equals t. And whereas this particular assumption here is saying that this only has to hold for those values of the independent variables at that particular time. And this assumption here is actually what we call, if I can fit it here, it's what we call weak exogeneity, opposed to the strict exogeneity which we needed for the Gauss-Markov conditions. The final assumption which we require for OLS to be consistent is we require no perfect collinearity amongst regressors. So there's no change between that assumption and what we had before for the Gauss-Markov conditions. And just writing this out in sort of full, I sort of said that if assumptions 1 through 4 are satisfied, then beta hat least squares is consistent. So as the sample size tends to infinity, beta hat tends to the true parameter beta. The fifth assumption which we require is that the variance of ut given my independent variables at that particular time, so I'm talking about contemporaneous values of the independent variables, has to be equal to sigma squared. And note again that this is less restrictive than the Gauss-Markov condition, because the Gauss-Markov condition here was that the variance of ut given all my values of my independent variables for any point in time s had to be a constant. So, and this was holding for all values of s, including the situation where s equals t. So this assumption here is less restrictive than that of the Gauss-Markov conditions. The final assumption, which is required for inference on OLS, is that the covariance of ut and us, or let me just rewrite that, us given xt and xs has to be equal to 0. And you probably guessed again that this is less restrictive than the Gauss-Markov conditions, which required that the covariance of ut and us, given my values of my independent variables xi and let's say xk, had to be equal to 0, where this was going to hold for all k, so this had to hold for all time periods. And if all of these assumptions are satisfied, not only is beta hat least squares consistent, it also behaves normally in the sort of asymptotic limit. So we can actually go about doing inference on our models when we have time series. And this is really beneficial because we can be much less restrictive than we were with the Gauss-Markov conditions, which are kind of idealized conditions which may not hold in reality.